The most distant human-made object, NASA's Voyager 1 spacecraft, is in interstellar space. Well, this just contributes to the number of discoveries that Voyager's been making.
Humans have a good grasp of how the universe works. Although we haven't ventured beyond the moon, our species seems to have a rather deep understanding of the cosmos at large. However, much of this information is based on hypotheses and assumptions. This is why space probes such as Voyager 1 and Voyager 2 are so important to our understanding of the cosmos. These probes are transmitting data to us in real time, thereby providing us with information about the outer regions of our solar system, which we may not personally explore for many decades to come. The Voyagers have been sending us information to process, and in addition to that, it has just delivered us a dreadful warning, and everything is about to change because of it. So join us today as we examine what the Voyager has encountered thus far, as well as the terrifying message and what it might mean for the future. The Voyager missions have been an integral part of space exploration for almost 45 years, during which time they have provided some of the very first and most significant glimpses into the actual state of our solar system. Despite this, when the initial plans for the probe were carried out, it was never intended that these missions would survive for such a long period of time. When Michael Minovich recognized that a spacecraft could piggyback on the velocity of a planet and catapult further out into the solar system, he had the epiphany that led to the conception of the idea to send out probes in the 1970s. This was a complete and utter accident. The Voyager program consists of two spacecrafts, Voyager 1 and Voyager 2. Voyager 2 was actually launched first, in August 1977, but Voyager 1 was sent on a faster trajectory when it launched about 2 weeks later. They are now the only two operational spacecraft in interstellar space, beyond the Sun's influence. In 1979, Voyager 2 passed Jupiter, Saturn in 1981, Uranus in 1985, and Neptune in 1989. It is the only spacecraft to have visited Uranus or Neptune, and it has contributed most of the data that we now use to characterize them. Voyager 1 overtook Voyager 2 just a few months after launch due to its faster speed and more direct course. It made a stop at Jupiter in 1979 and Saturn in 1980. In 1998, it surpassed Pioneer 10, the only other spacecraft in interstellar space at the time, and is now the farthest distant artificial object from Earth. The two spacecraft are identical in every sense, with 3.7-meter, 12-foot radio dishes to broadcast data back to Earth and a pair of 16 thrusters to adjust their orientations and direct their dishes toward Earth. The engines use hydrazine fuel, while the electronic components of each spacecraft are powered by plutonium-fueled thermoelectric generators. Each carry 11 scientific instruments, roughly half of which were designed specifically for planet observation and have since been turned off. Among the instruments that have been deactivated are many cameras and spectrometers used to study the planets, as well as 2 radio-based studies. Voyager 2 now has 5 functioning instruments: a magnetometer, a spectrometer designed to investigate plasmas, an instrument to measure low-energy charged particles, and one for cosmic rays, and one that measures plasma waves. Voyager 1 only has 4 of those, as its plasma spectrometer is broken. During their grand journeys of the solar system, the Voyagers collected tens of thousands of photographs and measurements that altered our understanding of the outer planets. At Jupiter, they provided us with our first in-depth ideas of how the atmosphere of the planet moves and develops, demonstrating that the Great Red Spot was a counterclockwise rotating storm that interacted with other smaller storms. They were also the first to detect a faint, dusty ring around Jupiter. Finally, they observed some of Jupiter's moons, discovered Io's volcanism, discovering the linear features on Europa that were among the first hints that it might have an ocean beneath its surface, and bestowing Ganymede with the title of largest moon in the solar system, a title previously held by Saturn's moon Titan. Following that, each spacecraft flew past Saturn, measuring the composition and structure of Saturn's atmosphere, while Voyager 1 gazed into Titan's thick cloud. Its discoveries led to the theory that Titan may have liquid hydrocarbons on its surface, which has since been confirmed by other missions. When the two missions observed Saturn's rings, they discovered the well-known gaps and waves. Atlas, Prometheus and Pandora, 3 previously unknown moons of Saturn, were also discovered by Voyager 1. Following this event, Voyager 1 departed the solar system, while Voyager 2 continued its journey toward Uranus. It discovered 11 previously unknown moons and 2 previously unknown rings. Many of the features found on Uranus remained unexplained, such as its strange magnetic field and an unexpected lack of large temperature fluctuations at different latitudes. Neptune was Voyager 2's final visit 12 years after it departed Earth. When it arrived, it continued its run of discovering new moons by discovering 6 tiny satellites and rings around Neptune. It observed the planet's composition and magnetic field, just as it did with Uranus. It also discovered volcanic vents on Neptune's massive moon Triton before joining Voyager 1 on its way to interstellar space. After its planetary encounters, Voyager 1 took the iconic pale blue dot image, showing Earth from about 6 billion kilometers, 3.7 billion miles away. However, during the course of the last 10 years, both spacecraft entered a new domain, known as the interstellar medium, which is a tenuous material that fills the immense space that exists between the stars. There, the spacecraft continues to make new findings. The strength and direction of the interstellar magnetic field have astonished experts, and the new data have even fueled debate about the geometry and activity of the heliosphere, the Sun's magnetic domain. Assumed to have the shape of a comet for a very long time, the heliosphere may really be more spherical than previously thought. And when sunspots grow and disappear, does it get bigger and smaller, or does it remain relatively the same? The spacecraft has provided some tantalizing hints in this investigation. When the solar wind, which is the flow of charged particles emanating from the Sun, comes to a halt, astronomers consider this to be the beginning of the interstellar medium. This ionized gas or plasma acts like a pebble in a stream, pressing against the cooler, denser interstellar plasma streaming around it. The sun-carved cavity is called the heliosphere, and its edge the heliopause, just as the top of Earth's troposphere is called the tropopause. According to Don Gurnett, a researcher at the University of Iowa in Iowa City who worked on the Voyager mission, we really didn't know how far out the heliopause was when the spacecraft was launched. Some speculated that the heliopause could be as close as Jupiter, which is only 5 times further from the Sun than Earth. As the spacecraft sped ever outward, estimates of the distance to the heliopause kept going up. It certainly wasn't at Jupiter, or Saturn, or Uranus, or Neptune. As a result, no one knew when or where Voyager would enter interstellar space. Gurnett said that shortly after the Neptune encounter, Voyager saw indications of heliopause in the distance. Both Voyagers started picking up strong radio waves at frequencies between 2 and 3 kHz in July of 1992. These radio waves were attributed by Gurnett and his colleagues to 6 significant flares that had occurred on the Sun more than a year prior to their discovery. According to the findings of the researchers, the plasma that was expelled during the flares finally made its way to the heliopause, where it caused electrons to oscillate and release radio waves. The frequency of oscillation is related to the square root of the electron density of the plasma, and the fact that the observed frequency of the radio waves implied a density matching that expected for the interstellar medium was significant. The local interstellar medium is far denser than the outer heliosphere, despite the fact that it is so tenuous that it could be mistaken for a pure vacuum on Earth. Furthermore, knowing the approximate speed of the outbound solar material and the length of time it took for it to hit the boundary revealed the distance of the heliopause from the Sun. This distance is between 116 and 177 astronomical units, where 1 astronomical unit is the mean distance between the Sun and Earth. However, Gurnett's claim was met with some resistance. To begin, such radio waves had never been observed by anybody before, and numerous scholars had doubts regarding Gurnett's explanations for the signals. Another implication of his measurement was that the heliopause was located at a distressingly great distance. By comparison, the distance between the Sun and Neptune is just 30 astronomical units, whereas the distance between the Sun and Pluto is, on average, roughly 40 astronomical units. Nevertheless, the spacecraft emerged unscathed from the ordeal. Voyager 1 passed through the heliopause on August 25, 2012 at a distance of 121.6 astronomical units. This is approximately 4 times the distance to Neptune and is completely consistent with the prediction made by GANYMEDE 20 years earlier. However, because the crossing generated so much controversy, NASA decided to delay the announcement of the achievement for 13 months. Despite this, Voyager did notice a few telltale signs that it had passed through the heliopause. There was a disappearance of high-energy particles coming from the Sun, which was probably a hint that the rest of the solar wind had been left behind as well. Additionally, after Voyager's passage, cosmic rays coming from beyond the solar system, which are partially blocked by the heliosphere, became more powerful. These signs alone, however, failed to convince many researchers. There were 2 different issues. First, the plasma instrument on board Voyager 1 had stopped functioning. Thus, the spacecraft was unable to record the sudden increase in particle density that occurred when it departed the heliosphere and entered interstellar space. Second, it was hypothesized that the magnetic field would point in a different direction beyond the heliosphere, but this did not turn out to be the case. To this day, the reason why the magnetic field outside the heliosphere coincides with the magnetic field inside has not been satisfactorily explained. Voyager's accomplishment was aided in part by the Sun. Solar storms had begun to erupt earlier in 2012, and the following year they shocked the plasma that Voyager 1 was traveling through. This caused electrons in the plasma to oscillate, which resulted in the emission of radio waves that the spacecraft was able to detect. The frequency of those radio waves showed that Voyager had entered a significantly denser domain. On November 5, 2018, Voyager 2 also crossed the heliopause. This time around, the passage did not raise any eyebrows. The plasma instrument on the spacecraft was operational and was able to measure the spike in particle density caused by the collision of protons, electrons, and other charged particles with the instrument. It also took note of the temperature, which ranged from 30,000 to 50,000 Kelvin and was significantly higher than the temperature of the nearby interstellar medium. This was most likely the result of the plasma being squeezed when it entered the heliosphere. The probe, just like Voyager 1, witnessed the disappearance of the solar wind and an increase in cosmic rays from beyond the solar system. But the magnetic field again failed to change direction, indicating that the result 6 years earlier was no fluke. But the thing that was most amazing to me, says Stamatios Tom Kremigis of Johns Hopkins University, was the fact that the crossing distance was 119.0 astronomical units. That's almost exactly the same distance where the spacecraft's twin had crossed, a surprise because the solar cycle was then in a different state. As sunspots wax and wane during an 11-year period, the solar wind strengthens and weakens, pushing harder and then less so on the heliopause, albeit with a temporal delay of roughly 2.5 years. As a result, the heliopause will expand and contract. Because the pressure from the solar wind was lower in 2012 than it was in 2018, the heliosphere should have been much smaller during Voyager 1's passage than it was during Voyager 2's. Instead, the roughly similar distances imply that the heliopause is more robust than previously anticipated, according to Kremigis. Whatever the exact form of the heliosphere is, Voyagers 1 and 2 continue to shoot away from it. Voyager 1 will be 155 astronomical units from the Sun by the end of the year. The signals from the spacecraft will take more than 22 hours to reach us since they move at the speed of light. Voyager 2 will be 129 astronomical units away and will pass the silent Pioneer 10 in late 2023 to become the second furthest spacecraft of all time. The 2 Voyagers are racing away in opposite directions, further apart than either is from Earth. Last year, scientists announced that Voyager 1 had recorded a humming noise that was linked to waves identified in minuscule amounts of gas found in the near emptiness of interstellar space. NICOLA, the director of NASA's Heliophysics Division in Washington, D.C., stated in a statement that the Voyager's mission has supplied significant information about the Sun and the Sun's influence throughout the solar system. Over the last 45 years, the Voyager missions have been critical in providing this knowledge and have changed our understanding of the Sun and its influence in ways that no other spacecraft can, Fox continued. Each Voyager is powered by a plutonium-based thermoelectric power system. As the plutonium breaks, the heat production decreases and the Voyagers lose power. To compensate, NASA stated that the team turned off all non-essential and several originally considered necessary systems. These include heaters that safeguard still operational instruments from the intense cold of space. However, the Space Agency states that all 5 instruments that have had their heaters turned off since 2019 are still operational. NASA experts are still puzzled as to how the Voyagers can continue to operate in temperatures well below what they were built for. A problem occurred with the probe's Attitude Articulation and Control System, AACS, in the previous year as well. This was the system that ensures the antennae on the probe are aimed in the direction of Earth. The probe had an impeccable track record up until this point without any known interference. The muddled probe started sending back inaccurate telemetry data through an onboard computer that had stopped functioning years previously, which caused the proper data to become corrupted. This caused the probe to become confused about its position in space. Even though NASA experts were just recently able to solve the problem by directing the system to revert back to its previous computer, the Voyager's slip raises the question of whether or not it is time to retire one of the agency's oldest and farthest traveling space probes. Even though the government has stated that the inaccuracy does not pose a risk to the mission's continued viability in the long run, several scientists have already begun looking into the possibility of developing Voyager's successor. According to Ralph McNutt, the chief scientist for space science at the Johns Hopkins University Applied Physics Laboratory, we've gotten incredibly lucky with the Voyagers, and the fact that the things are still working as well as they are is really a combination of a technological miracle and some luck. Therefore, it should not come as a surprise if something goes wrong. McNutt, who was fortunate enough to be present at Cape Canaveral, Florida during the launch of Voyager 1 in 1977, is the principal investigator of a team at the Applied Physics Laboratory that has recently submitted a detailed proposal to NASA for a mission concept that could significantly exceed the limits of Voyager. The proposal is for a mission that could explore more distant parts of the universe than Voyager did. Their spacecraft, which they have given the name Interstellar Probe, would be able to travel even further than the Voyager missions did, all the while continuing to investigate the heliosphere, the bubble-like region of space that protects our solar system from galactic radiation. With the right technology, McNutt's concept for a probe could be ready to launch between the years 2036 and 2042. The exact year would depend on when it would be able to receive a gravity assist from Jupiter, which is where the orbit of the craft would use the planet's gravitational pull to slingshot itself into the outer reaches of space. It is possible that the Interstellar Probe mission will wind up breaking the record set by its predecessor for the furthest distant human-made object in the universe. This would be the case if the mission is successful. And in contrast to the 45-year-old Voyager, which has already outlived its intended mission lifetime by a factor of 10, according to McNutt, the Interstellar Probe would be reliable enough to last for at least another half-century. But even if we were to launch, it wouldn't happen for a few more years. Although NASA funded the initial study, the concept is still in its early phases and will not be made into an official mission until it is examined and selected by a decadal survey committee, the conclusions of which might take another 2 years to complete. But if astronomers now have access to powerful observatories like the James Webb Space Telescope and the long-awaited dark matter hunter, the Nancy Grace Roman Space Telescope, then why exactly do we need probes? The explanation is as straightforward as the fact that various missions frequently have contrasting capabilities and priorities. Voyager and the Parker Solar Probe are examples of heliophysics missions which investigate the Sun's influence in space. In contrast, the James Webb Space Telescope and Roman are examples of astrophysics missions, which investigate things like exoplanets and distant galaxies. Despite their distinctions, probes and larger survey telescopes, such as the JWST, are two sides of the same coin. Both of their discoveries are necessary in order to paint an accurate and comprehensive picture of our place in the cosmos. Coming back to the Voyagers, each Voyager spacecraft includes a golden phonograph record attached to its side, which is meant to serve as a time capsule from Earth to any extraterrestrial life that may discover the probes in the distant future. They are imprinted with a message from Jimmy Carter, the US president at the time of launch, which reads, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts and our feelings. We are attempting to survive our time so we may live into yours." The record's covers feature many images, including visual directions on how to play them, a map depicting our solar system's location in relation to a group of 14 pulsars, and a representation of a hydrogen atom. They are plated with uranium, and the rate of decay will allow future discoverers of each record to compute when it was made. The contents of the records were chosen by a committee chaired by Carl Sagan. Each contains 115 images, including scientific representations of the solar system and its planets, Earth's flora and wildlife, and instances of human culture. Natural noises such as breaking surf and birdsong are included, as are spoken greetings in 55 languages, an hour of brainwave recordings, and an eclectic range of music ranging from Beethoven to Chuck Berry to a variety of folk music. No one knows how much longer the two spacecraft will survive. They have to stay warm so that the fuel they need to keep their antennas pointed toward Earth doesn't freeze. Voyager's heat comes from plutonium, but as the radioactive element decays, it provides less and less power every year. Despite being further from the Sun, Voyager 1 is the warmer spacecraft. There's a story to that, Cremegis explains. After NASA launched Voyager 2, engineers realized that it was colder than intended, so they added extra insulation before launching Voyager 1. That extra warmth could help the spaceship live longer, and because Voyager 1's plasma instrument has failed, it consumes no energy, leaving enough for heating the spacecraft. As a result, the Voyager that's exploring a more distant and hence more likely interesting region of space may continue to return data even after its mate falls silent. Let's hear your thoughts about these remarkable spacecrafts in the comments below.